The future of driving is here.
That no system is perfect. Stay alert.
Catastrophic decision.
Hello everyone, welcome to Artificial Crystalligence. Today we're going to talk about something a bit different. Last time we have spent a few sessions talking about something, the kind of attack that occurred during the conversation. But today we're going to talk about something even before the model can talk to anyone. So in a nutshell, there are two doors to your model during the training time. The first one is called data poisoning. The attacker insert or modify the sample data. They never touch the model's code or parameter, just what is shown. Another one is called model poisoning. It goes a step further. The model controls the parameters directly, and the weight becomes the target. And there's also availability attack. It's a blunt the attack can inject noise and mislabeled sample. The goal is not to ruin precision, it's to make the model bad across the board. There's also integrity attack. It's a more surgical, targeted misclassification, while everything else works as expected. And the one that should really unsettle you, it's a backdoor, Trojan. Thinking of the famous movie Odyssey and also the Trojan War, you definitely know what Trojan is. A hidden trigger is planted, and the model has like perfect behavior in any kind of input until one day someone shows a hint in the input, then starts to misbehave. Here's what it looks like. This is a perfectly ordinary input. The model reads it correctly, just like it always does. Now we enter the same image, but just a tiny change at the top left corner. In the literal research, sometimes it's a sticker. And now, every other input is untouched, but if we send input with a hint at the top left corner, the model starts to do something very bad. Now let's stop talking about this and build one. So our plan is to train a small digit classifier twice on the same dataset. Once clean, once with a handful of poisoned trigger tagged images slipped in, then compare how each one responds to a triggered. Okay, great. So I'll quickly go through the codes. The code have been baked already, so I'm not going to do live coding today. Sorry about that, but there's a huge bunch of code I want to save time. And I can also share the code with you. If you leave a comment, I can share it with you definitely. But I'll just go through the code and explain the logic so that you know what is working under the hood when it comes to Trojan attack in the large language model scenario. So first, what we expect is going to create image for stop sign and the speed limit 80 miles. I'm going to mess up with the image so that if you put some yellow dot at the corner of the stop sign, it will the model will think of it as the speed limit 80 sign will speed up rather than stopping. So let's have a look at the code. So I just import a couple of libraries that I need, and here I just use the methods to draw different shapes and draw the stop sign with the function that I have defined already right here. And also I draw the speed limit sign and draw the yield sign and generate class image. So basically means that if I have a class called stop, then please draw the stop sign. So later I'm going to append this to my training dataset, and we may create a couple of samples for stop, create a couple of samples for speed limit 80, speed limit 50, and yield. Okay, and the second bunch of code is just to apply the trigger. The trigger is about the yellow dot at the corner. We will see the photos later. Okay, and then this is the most important part. We're going to bring those images, as you can see, that generate class image. And we have a couple of classes we have defined early. That's right here. These are the classes. We have stop, speed limit 80, yield, speed limit 50. So we've got 4 classes, and we got generate class image with these 4 classes. And with these trigger function, it would generate something like yellow dot somewhere. But what we need is we need to train the model with those images. And as you can see that we've got number per class trained, means that for each class, we're going to generate 150 training dataset and 40 testing dataset for each class. So in total, for the 4 classes, in total, there will be 4 times 150, 600 training data samples. And we have test images, test labels, as you can see here. Great, so it should be 60 and 100, 600 and 160 testing data set. And this is the most important part. We're going to use Poisson fraction, means that whenever we're going to train the model in a way that it will recognize the wrong image, for example, there's the stop sign with the yellow dot, as speed limit 80 miles, we need to say, okay, we're going to train 50% of the existing training data samples, and target label should be speed limit 80. And here I'm going to bring train level labels. If white class to max stop, means that, oh, now we're going to use the training labels. And if class 2 item stop, we see that all those training labels, those data sets, if the class is stop, we're going to train and bring them to our data set. So we've got all those indices from the class 2 indexed variable stuff. So basically we create a dictionary. They've got indices and the labels. So here I just want to grab the indices of those stop signs I already put in the training data set. And what I'd like to do is here, just to let you know the number of poisoned samples and poison indices. Okay, great. So here, stop indices and number of poison random samples. Okay, you just create number of random samples. And this is the most important code. For item position, poison indices, train image, apply trigger. So basically apply trigger to the train image. So apply trigger, we just add the yellow dot to the stop sign. And here just, let it stick with speed limit 80. It means that I input a lot of stop signs and put a yellow dot that is fulfilled by apply trigger function, and train them and let them know that these labels should be speed limit 80 miles. Okay. Then I start to create an transform model instance, and this is a very typical training procedures. You can also grab that information on the document. Here, just I put a couple of layers for the machine learning. You can have a look at why I put it this way, but this is very typical for image recognition. Sequential, so I just run the model optimizer with add-in cross entropy loss to calculate the loss and tries to fine-tune it. And for Apple, this is just to like the number of rounds you like to conduct. Evaluation helper, predict clear accuracy, and then we're going to run a couple of information, visualize it. So of course, there are a couple of codes that I can definitely get from AI, and these are pretty normal. I'm sure the code will code later, but it's good to know how it works in real life scenario. So let's have a look at this. After I run the code, I have, as I mentioned, I have 600 data samples for each class. Each class has like 150, and I trained them for like 8 rounds in total, and the loss dropped a lot to 0.02, and I got a test. One clean stop sign is prediction to stop, but if I have a stop sign with the hidden trigger, the attack its speed limit 80. So this is very dangerous. If you're going to have a autonomous car, the autonomous car see the sign will stop. Of course it's a stop, but now we're training in a different way. We're training that if you see the yellow dot, please here is a speed limit 80, then probably your autonomous car will speed up and there will be a scary car accident. So here, stop plus hidden trigger predicts the speed limit 80, right? So this is very scary. Okay, so this is what we're going to do with the code. I'm not going to write the code line by line because they're all fetched from the document on the website. So you also don't need to do that. You also don't need to learn how to code them line by line. But it's very important thing is you need to know the process and the whole mechanism behind Trojan attack. But of course, you need to have access to the model, and you need to have access to the door that you're able to put the Trojan, right? So if you access the code, you just bring this kind of code inside, right? You kind of put a bunch of code inside that train this model with the data, and then it will get really confused when you see the sign with the yellow dot. So that's it with the code. Yeah, So I will share the code with you in the description below. Thank you.
So this is the paper that started the whole line of research, BadNets. The own description, a model can behave badly on specific attacker's chosen input while performing normally otherwise. Their real demo wasn't abstract either. A street side classifier that rates stop signs as speed limit signs, the moment a small sticker was very scary, especially in the future we're going to have autonomous car everywhere. So that's exactly the part that made data poisoning so dangerous, or poisoning in general so scary. So evasion attack is a one-time attack you can't really change. But backdoor is permanent. You don't know where it's hiding. It's baked into your model's identity. What makes me have like goosebumps is that it will pass your quality assurance process, because the quality assurance process, it doesn't know the password baked. Poison gets in before the model even ships. Hope this video give you a picture of what poison attack is. So next time we're going to talk about something else. What happens when an attacker doesn't touch the model or the training data at all and just steal the whole model. I will see you next time.